All right, so when we kind of thought about inertial reference frames, there were a couple of things that were absolute. Space and time, right? When we looked at things in an inertial reference frame, those were what we called absolute. They were the same across the two reference frames. What if they're not? So in this mini lecture, we're going to kind of do this super fun, cool experiment, thought experiment, walking through what does all of this mean in thinking about Newton's theory of special relativity. So let's imagine, and we're going to look at this example of things happening at the same time. Two events happening at the same time, okay? So what does that look like? Let's kind of go to we have an observer. We're going to call that observer 1. Okay, eventually we're going to have two different observers, and we're going to think about what does it mean for things to be happening simultaneously. And observer 1 is standing between two events. So event A and event B. So in space, they are equidistant from event A and event B. And that event is going to be related to light, so something that travels really, really fast, okay? So let's say we have a lightning strike or a flash of light, okay? Flash of light at A. At the exact same time, there's a flash of light at B. Now, if observer 1 is directly in the center, then that light is going to travel, and it doesn't really matter what, light travels is constant, right? The light's going to travel, and it's going to hit observer 1 at the same time. So these two events, they're happening exactly the same time, hit observer 1 at exactly the same time, okay? And observer 1 can say, okay, event A and event B happened at the same time. Does that make sense? Okay. What if we have two observers now? And one observer is moving relative to the other observer. Okay? So now let's imagine that we put observer 1, hopefully this makes sense. I'm just going to erase it because I didn't really draw it in the best spot. Okay, so we have observer 1. And I kind of do it in the middle of the board. So here is, let's imagine they're on a high-speed super rocket. Okay. So observer 1 is here on this high-speed super rocket. And observer 2 is here on this high-speed super rocket. And if they're both stationary, and let's say our events A and B, so here's A and B, and here's A and B, are happening on at these same locations on the super rocket, okay? So at the edges of the rocket. And both of them are stationary, and A and B are simultaneous events. They happen at the same time. One observes the events, they hit one at the same time, two, those events are hit at the same time. So both 1 and 2 observed events. That's the same thing we just drew over here, right? So if I imagine, we're just going to use like a little wavefront as our example, okay? So here's a couple of wavefronts coming from A and coming from B, and if observer 1 and observer 2 are directly in the center, then they are going to have those wavefronts, the light, hit them at the same time, saying they happened at the same time. Now what if observer 2, observer 2, I was looking at the B, what if observer 2 is actually moving? So now imagine that, I'm going to draw this below, that observer 2 is moving. So right as the two observers pass each other, A and B happen. Okay? But observer 2 is now moving. So as that light traveled, so we observed that much. So here observer 2 is now. So this is with observer 2 moving, okay? I'm going to use observer 1 as my reference. These are where at the same time, that's where those lights are going to have appeared at that point in time. And so observer 2 has not yet gotten the light from A and has already gotten the light from B. So it's already passed through the light from B, and it hasn't yet gotten the light from A. Okay? So from observer 1, they say simultaneous. They're going to say A and B were simultaneous. Observer 2 is going to say B happened first. Okay? So observer 2 sees B happen before A. Observer 1 says, no, they happened at the same time. Who's right? Well, they both are. So if light travels regardless of whether these, right? This has to do with light traveling also. Regardless of whether these two are moving or stationary, the light is going to travel a certain distance in a certain amount of time. A and B, observer 1 is going to say they happened at the same time. B is going to say, B happened first. So they're not simultaneous to B, and they are simultaneous, to observer 2, and they are simultaneous to observer 1. So simultaneity is not absolute. Both of them are correct. And if simultaneity is not absolute, then time can't be absolute. If both of them are correct, and one's not better, one reference frame isn't better than the other, and simultaneity is not absolute, then time can't be absolute. And so that's what the theory of special relativity tells us, that time is not absolute. Okay, we're going to look at another thought experiment. What does that mean? If that's the case, then how does time change depending on if I'm moving? And so we're going to look at that in the next video. It's kind of fun. It's fun to wrap our head around. All right, good job.